Hello, in this video I'm going to talk about area and the definite integral. So in this chapter we look at the area beneath a curve from A to B, and we have this curve f of x that we're looking at. Now we can see that this doesn't really form a nice shape, but we can see that we can pick a part of it of where we just inscribe a rectangle. Now the idea behind calculus is that we do this a bunch of times until the area fits underneath the curve. So essentially we have that we're just trying to estimate the integral from a to b of f of x, and we're going to say that this is approximately, so essentially we're just going to add a bunch of rectangles from 1 to n, but we're going to take their heights. Okay, so we're going to take their heights and we're just going to multiply that by their delta x's. So that's going to be delta x. And normally we would put delta xk. Now, in essence, what's going to happen is that what we can do is we can actually say that the delta x k is equal to the difference of b and a, or b minus a, all over n. Now notice that if n goes to infinity, this delta x goes to 0. So what we want essentially is that these rectangles become so smaller that it ends up fitting underneath the curve. Now, this symbol right here, all that means is it means just to add. Now, what we have here on the right-hand side, this is what we call a Riemann sum. Now, a Riemann sum is basically, just calculating the area that lies beneath the curve from A to B, and eventually you'll take n to be very large. Now, in some cases, what we can have is that um, the shape is actually something that we can work with in terms of like geometry. So imagine if we had a shape of a region underneath a curve or bounded by a curve that was like a circle, so that's just pi r squared, a rectangle, length times width, a triangle, base times height divided by 2, or even a trapezoid, because we could have that, we can inscribe a trapezoid within our region, because like I could have something like this, but what if we chose like just, we have a point right here, and maybe we have a point right here, but if we like draw a line from here, and then we have that this is the rectangle that would lie beneath it, then in that case this is going to be useful in terms of using like area of a trapezoid. So we have like this example where we have the function f of x is equal to 4x from 0 to 8, and we're going to divide it into what we call partitions. So n is equal to 4. Now, I mentioned that basically that we can find the delta x. The delta x, it's all going to be the same. It's going to be 8 minus 0 divided by 4, and that gives us to 2. Now I use this term partition because basically what's happening is that we're dividing it into pieces or subintervals. So we have from 0 now to 2, and then to 4, and then to 6, and then to 8. Now, if I want to find the area beneath this curve, I have to pick points either on the left or the right, for that matter. So for instance, let's say that we want to look for the left sum. Well, the left sum is basically just taking all of the values that are all to the left with exception of the 8. So that's going to be that the area is approximately equal to 2 times f of 0 plus 2 times f of 2 plus 2 times f of 4 plus 2 times f of 6. Now, note that basically there's a common factor of 2, but we can actually look at this. We have 2, times 4 times 0 plus 2 times 4 times 2. And then we have 2 times 4 times, let's see, well, we're doing 0, 2, and 4. And then we have 2 times 4 times 6. Okay, so we can actually say that, for example, that either we can use some form of factoring or not. I was going to use factoring, but I mean, these values, they're not too bad, so maybe we can just go ahead and see what we get. So we have, that gives us 0. That gives us 16. This gives us 32. And then we have that this gives us 48. Now, if I add this up, I end up with 96 units squared. So that's telling me that the area beneath the curve is approximately 96 units. Now, if I wanted to find a right sum, well, the right sum is basically gonna be where we just look at the values. So, like for example, if we know that the partition um, is such that you want it to pick the right endpoints, you're picking everything except for 0. So then that means that you would be plugging in 2, you'd be plugging in 4, that would be 4, and then you'd be plugging in 6, and then you'd be plugging in 8. Now, in this case, note that basically we basically already have kind of like everything else except for the 8 that we just need to add on. So if you want to do it like that, you can. So I have that the area is approximately equal to 2 times f of 2 plus 2 times f of 4 plus 2 times f of 6 plus 2 times f of 8. Now, I mentioned that I already have basically this computation from 2 to 6, which is 96. So we have 96 plus 2 times 4 times 8. Okay, so this is 64. So that's 96 plus 64. But this is equal to 160. So we have that this is going to be 160 units squared. Okay. And then again, we plugged in 8, and it was times, let's see, just to make sure. Yeah, so we plugged in 8 times 4, which is 32, times that is 64, and then we just added. Now, one thing that we can look for example, is what we call the midpoint sum. So the midpoint sum basically is like where we try to minimize the overage and the under. So we have that the midpoints, we're only going to plug in. So if I just go ahead and write down the partition, you'll note that basically the endpoints, the midpoints, are going to be 1, 3, 5, and 7, respectively. So basically we're just plugging that into our equation. So the area would be approximately 2 times, now the function value is basically just like 4 times 1 plus 4 times 3 plus 4 times 5 plus 4 times 7. Now note that basically this is just really 8 multiplied by 1 plus 3 plus 4, not plus 4 but plus 5, and then that's plus 7. Now interestingly enough, we know that basically that this equals to 16 times 8 is 128 units squared. Now, why this is interesting for me is that this is actually the true area for the area beneath this curve. The reason that I know that is because I have that this is going to be 8 as the base, and we have that this is going to be 32 as the height. So what that means is that we could have just said, okay, well, we have that area is 1/2 multiplied by 8 multiplied by 32, but basically this gives us 128 units squared. So this way is a lot easier, obviously, but we can actually do it the exact same way if we, use our estimates in this case. Now, for those that might be going a little further, if you take the average of the left sum and the right sum, you actually do get the the trapezoid sum, which is actually the same as the midpoint in this case, but it's because of the nature of like the geometry of the uh, of the region. Now, the thing of which that we're trying to essentially define is that you know if we're trying to say that the area is basically just equal to the integral from a to b of f of x dx, well, basically we have to essentially just apply the limit to our sum that we're doing. So we have that this is the sum from k equals 1 to n, and that's going to be f of xk star times delta x star, not star, but k. Now, what we know is that basically that this is the same for all of the rectangles. It's just going to be b minus a over n. But this what I'm boxing right here, this is what we call the definite integral. So we have that this right here is what we call the definite integral. But notice that it's just the limit of all of the Riemann sums from 1 to infinity. So we have that in this case, the only difference is really that you took a limit as n tends to infinity, and that now you have that there's equality. And that's pretty nice in this case. The difference, though, is that the choice of xk star, it's basically anything. So it could be um, a left endpoint, or it could be a right endpoint, or it can be a right endpoint, or it could be a midpoint. Okay, now in this case, if n is really large, in actuality, it doesn't matter. So if we kind of like just think about, the region of which that you're looking at, really, it does not matter what, it doesn't matter about like midpoints, left points, and so on, because the logic is that you're using so many intervals that at that point it doesn't really matter like what point it is. Okay. The main thing though that you should take away from this is that the point xk star, it is actually contained within the subinterval xk minus 1 comma xk. So in this case, like if you go back to those examples, you'll notice that those points were contained within specific intervals. And what determines the intervals is basically just the size of n. Okay, so this is actually just a repeat. Yeah, so it's the left, the right, and the midpoint. And we have that delta xk is the difference of xk and xk minus 1. Okay, now right here you'll see that there's a problem that's already written out. You have that you're dealing with a function f of x equals to 3x squared from 0 to 4. You want to find the area from the given closed interval using n equals 8, and we're going to use left endpoints. Now I went ahead and found delta x, which is just 4 minus 0 divided by 8, which is just a half, which basically means that you're going from 0 to a half to 1 and so on. Now, interestingly enough, okay, so we're saying that this is approximately going to be equal to the Riemann sum with n equals 8. But you'll notice that basically it's not going to be exact. Okay. Now, if you're more visual in terms of like, what do you want to see, or if you would like to see like what's going on, you can actually just draw the parabola. So this is a parabola. Okay. Now, we'll say that, from 0 to 4, that maybe like this is what it looks like. So in this case, you have that the region is like just right below the curve, the parabola. Of course, like you can make the scale a little bit bigger. Okay, now our area, it's going to be approximately, so the delta x is the same, so it's just going to be 1/2. And then we have that the nature of the graph is 3, so it's going to be times 3, but then multiply that by the left endpoints. So you have 0 squared plus 1/2 squared plus 1 squared plus 3, yes, 3 halves squared plus 2 squared plus 5 halves squared plus 3 squared plus 7 halves squared. Now, this is a little weird because basically notice that this is really 2 over 2. Notice that this is really 4 over 4. Okay, now the reason that I'm saying that is because like we can take out a fourth. So this is going to be equal to 3/8 multiplied by 1 squared plus 2 squared plus 3 squared plus 4 squared plus 6, no, plus 5 squared plus, right, so that's 6 squared plus 7 squared. Now you can go ahead and multiply all of this through to see like what it is. Um, but what you're basically gonna get is that when you add up all of this, you're gonna get that this is going to be let's see, 3 times 3/8 multiplied by 140. And then from there, you'll get that this is approximately 52.5 units squared. Now, in no way is this really close at all to the actual area because I can actually work out that if I was to basically show that I have the limit as n tends to infinity for uh, k equals 1 to n of, let's say, like 3 xk star squared, and then I have delta x k. Accordingly, this is equal to the integral from 0 to 4 of 3x squared dx, but this is really equal to x cubed from 0 to 4, which is actually equal to 64 units squared. Now, this is actually way easier than doing, obviously, like the Riemann sum, but, this is just the beginning, you're just approximating and things like that. So, if you were to try like a big number like n equals to 100, eventually it's going to get close to 64 because essentially you're minimizing the error by making n larger and larger and larger. But in the next chapter, basically you're just going to do where you take the antiderivative and then you just evaluate from top minus bottom, because basically I did 4 cubed minus 0 cubed, which is 64. So we can see that we are way off in terms of this, okay? Now, essentially, just be sure that you go ahead and you work examples where the n is, a little bit bigger, or if you're using different points like left, right, or midpoints and things like that. And that's going to be it.